This will be our last example of this lesson. We're going to show you a two-tailed hypothesis test. In 2001, 23% of American university undergraduate students had at least one tattoo. A health practitioner suspects that the percent has changed since then. She obtains a recent random sample of 1,026 university undergraduates and finds that 272 have at least one tattoo. Is this sufficient evidence to conclude that the percent has changed? And we're going to let our significance level be 0.05. So the first question I want to ask myself when I start to formulate my hypothesis statements is this about a means, the question, or is it about proportions? Let's back up a bit. If we look here, we don't see the word proportion outright, but we do see the word percent several times over. And here in this sentence, she obtains a recent random sample of 1,026 and finds that 272 have at least one tattoo. So this is the type of evidence that supports a proportion. The students answered either yes or no, they have at least one tattoo, and that categorical response is then treated as a proportion for us. So our answer to this question is proportions. So what we're going to do now is try to formulate our null and alternative hypothesis. The proportion that the researcher wants to compare to is the 23% that was known back in 2001. So our null hypothesis, P for proportion, is equal to 0.23. She's not sure what's happened in the many decades that have passed. She just wants to know if the proportion has changed. That lack of clarity of increase or decrease leads us to use the not equals to as our alternative hypothesis. So we have a few assumptions and conditions we need to check before we head on and do some sketching and eventually head to StatCrunch. With a one proportion hypothesis test, we want to make sure randomization was there, and the researcher did choose a random sample of the undergraduates. Independence, we're going to need to assume that each undergraduate's tattoo status is independent of another's. I think that's easy enough to assume. And finally, the success and failure condition. We want to make sure that n times p is at least 10 and n times q is at least 10. 1,026 is our sample size n, 0.23 is p, as stated in the hypothesis. And if we multiply the two of those together, we'll check that they're greater than or equal to 10. And then q, the probability that a student doesn't have at least one tattoo, is 0.77. So you multiply that by the 1,026, and both of these numbers are well above 10. So all of our assumptions and conditions check in this case. So that tells us we can use the normal model to solve this question. So again, as you've seen me do 2 times before, I like to sketch the problem before I head into software. So I'm going to give myself the normal model we just spoke of with 3 tick marks out to the edge. And I'm going to proceed to label this. Now, what our null hypothesis tells us, the 23% or 0.23 is the middle of our model, is the mean. I'm going to have to pull out my scientific calculator and calculate this. Went ahead and did it ahead of time, but we're going to multiply p times q divided by n. Of course, that's under the whole fractions under a square root. This will give us the distance between the tick marks here, successive tick marks. We're going to move out by 0.013 each tick mark. Now I went ahead and did that to the right. Might want to pause and check my mathematics. I think I did it right. And I subtracted 0.013 every tick mark to the left. So this is the model according to the null hypothesis. What I would like to do here is to, now that we have the model built with the null assumed to be true, I want to insert the data, what the researcher found, her evidence. So if you remember, 272 of these graduates said that they had a tattoo, at least one tattoo. And that works out, if you divide that out, to 0.265, or about 26.5%. So if I look along the number line, I'm going to want to insert that information in the proper spot. So it looks like it fits naturally right before 0.269, but after 0.256. And I'm going to shade to the right, because we always go to the extreme, out to the edge from our evidence we observe. And I have this yellow area that's going to be my p-value. Now, this is a bit of a twist from our last two problems. If the alternative hypothesis is not equals to, we have to assume that this sort of 3.5%-ish difference here from the middle out to the edge, or 0.035 difference, could have happened to the right, or it could have happened to the left. So it could also be over here. So all I did here was draw a mirror image that's supposed to represent the same size as this area is to the right. We have the same area to the left. So I just went there. And as you can see, sort of popped in before I could talk about the mirror image. If we look at the number of tick marks away, 1, 2, and a bit, not quite to the third, but well over 2 tick marks away. So our z-score, our z-stat in this case, is greater than 2. And if we go out that same distance to the left, you can see we've gone that same distance, and this represents supposed to be a very similar size area, the yellow and the green. Now, the p-value that you use to solve this problem incorporates the area in both tails. So it's not just the yellow as your probability, it's also the combined green. And software will do this for you. Speaking of software, let's see how we can get this in. So we'll go to StatCrunch, to just a plain spreadsheet window. We'll click on Stat, Proportion Stats, One Sample with Summary. For our successes, we'll have 272, 1,026. Set up our hypothesis. So notice as I type in 0.23, it's repeated below. Both of these have a p there, as I was expecting. And of our 3 choices, we are choosing the not equals to. So we've let StatCrunch know the evidence and the hypothesis statements. That's enough for it to compute the needed values. Here's our results. See the hypothesis repeated back to me. The 272, the 1,026, just making sure I data entered everything incorrect. And here's our expected z-score that is well above 2 standard deviations away, or 2 tick marks away, almost at 2 2/3 tick marks away, 2.67. And the p-value that is in both that yellow and green region is essentially 0.0075, quite small. As we saw, those regions were quite small where we shaded. So let's take this 2 pieces of information and record it here. So our p-value was 0.0075. We want to compare that to the alpha they gave us. So the threshold of unusual was at 5%. What we observed in these 1,026 undergraduates is something far smaller than 5%. So our p-value is less than alpha. Therefore, we will reject the null hypothesis. Last step, make a quick statement summarizing our findings. Let's remind ourselves of the hypothesis statements. It always helps me when I write a statement to remember what my hypothesis statements look like and also what we ended up doing. Remember, we rejected the null, so I have crossed it out. It is no longer assumed true, which leaves us, well, the alternative. The alternative says that p is not equal to 0.23. I'm going to think about that as I write my statement. My statement will say, the sample data suggest that the percentage of current undergraduates that have a tattoo has significantly changed.